In this section we are going to dealing with inner product spaces. An inner product space is a vector space with an inner product which is a function that takes two vectors in a space and returns a real number. Inner product is a generalization of the concept dot product of vectors. An inner product must satisfy these four properties. First property is inner product x plus y z is equal to inner product x z plus inner product y z. Second property is inner product alpha x y is equal to alpha into inner product xy. That is, we can take a scalar outside to the inner product directly from the first component. Okay. Third property says that inner product xy is equal to conjugate of inner product yx. Fourth property, inner product xs should be greater than or equal to 0. Last property is inner product xx is equal to 0 if and only if x is equal to 0. So this says that if we are given an inner product, from that inner product we can construct a norm like this, that is norm x is equal to square root of inner product xx. Let's go through some examples. These are some other properties of inner product. These can be proved by using these fundamental properties of inner product. So these are some examples. Before considering the generalized form, that is Rn, let's consider first R2 and C2. So let's consider C2. So consider C2 over C, which is equal to collection of all pairs x1, x2 such that x1, x2 are complex numbers. So here we define inner product xy. So let's take two elements, x is equal to x1, x2 and y is equal to y1, y2 from this C square. So let's define inner product xy is equal to x1 y1 conjugate plus x2 y2 conjugate. Okay. So in Cn we can generalize that. So Cn will have n components. Each element in Cn will have n components. That is, here x will have n components, psi1, psi2, etc. psi n, and y will have n components, eta 1, eta 2, etc. eta m. So inner product xy is here defined as psi1 into eta 1 conjugate plus etc. plus psi n into eta n conjugate. Okay. So let's consider C square again. Now we need to show that this will satisfy all the 5 properties of the inner product. So first we need to show this property. For that we need an extra element z. So let's take z is equal to z1, z2. So the first property is inner product x plus y z must be equal to inner product xy plus xz plus inner product yz. That is, we can split this inner product in between this addition. Okay. So here x is this and y is this. So what will be x plus y? X plus y will be equal to x1 plus y1, x2 plus y2. So by the definition of this inner product x plus y z will be equal to For the first element x, we need to take x1, x2. For the second element y, we need to take its conjugate here. So here it will be equal to x1 plus y1, that is the first. So into z1 conjugate plus x2 plus y2 into z2 conjugate. Expanding the bracket, we can write it as x1 into z1 conjugate plus here x2 into z2 conjugate plus y1 into z1 conjugate plus y2 into z2 conjugate. So this term is inner product xz plus the next terms are inner product yz. So the first property is satisfied. Let's check what is the next property. Next property is inner product alpha xy is equal to alpha into inner product xy. Okay. So let's start the second property. Second property is inner product alpha xy is equal to alpha into inner product xy. We need to check this property. So x is x1 x2, so alpha x will be alpha x1 alpha x2. So alpha x is equal to alpha x1 alpha x2, sorry. So what will be inner product alpha x y will be equal to, by using this definition, it is alpha x1 into y1 conjugate. For the second elements, we need to take their conjugate components plus alpha x2 into y2 conjugate. So we can, here alpha is common, so we can take that alpha outside. So it is x1 into y1 conjugate plus x2 into y2 conjugate. So this will be equal to alpha into inner product, this is xy, inner product xy. So that property is also satisfied. Now let's check the next property. Inner product xy is equal to inner product yx the whole conjugate. Okay. So next property, we know that inner product xy is equal to this. Let's check what is inner product yx. It will be equal to, here the second element is x, so we need to take the conjugate components of x. Okay, so y1 into x1 conjugate plus y2 into x2 conjugate. Now what will be inner product yx whole conjugate? It is equal to taking the conjugate of this, and by using the property of conjugate, we can split it in between the addition whole conjugate. It is equal to y1 x1 conjugate whole conjugate plus y2 x2 conjugate the whole conjugate, or we can write it as y1 conjugate x1 conjugate of conjugate, which is x1, plus y2 conjugate x2 conjugate of conjugate is x2. So this is equal to inner product xy itself. Now let's check the next property. What is the next property? Inner product xx must be greater than or equal to 0. So what will be inner product xx? It is equal to, here the first element is x, the second element is again x. So when we consider x as second element, we need to take the conjugate of its components. Okay, so x1 into x1 conjugate plus x2 into x2 conjugate. So this is equal to mod x1 square plus mod x2 square, because z into z conjugate is equal to mod z square. So this is these are positive numbers, these are always greater than 0, so inner product xs is greater than or equal to 0. Now what was the next property? Inner product xx is equal to 0, we need to show that if and only if x is equal to 0. So inner product xs is equal to 0 means the terms is equal to 0. So these are greater than or equal to 0, so these are equal to 0 means each term must be equal to 0. That is mod x1 must be equal to 0 and mod x2 is equal to 0. Conjugate of, modulus of x1 and x2 is equal to 0 means each number x1 and x2 must be equal to 0, which implies x is equal to 0. So that property is also satisfied. So we can conclude that this is an inner product in C square. Okay. Similarly, in the case of R2, which means that collection of all x1, x2, where x1 and x2 are real numbers. Okay. In this case, similarly we can define inner product xy is equal to x1 y1 plus x2 y2, and we can show that this will satisfy all the properties of inner product. So this is an inner product in R2. Also you can verify that this is dot product, that is this is simply x dot y. That is as I said earlier, inner product is the generalization of dot product. So here that inner product space, instead of R2 and C2, here we consider Rn and Cn, and we can easily verify that this inner product will satisfy all the 5 properties. Next topic is orthogonality and orthogonal bases. Two vectors are orthogonal if their inner product is 0, which means that we know that two vectors, suppose consider two vectors in R2, we say that these vectors u and v are orthogonal if the angle in between them is 90 degree, or we say that u dot v is equal to 0. So as I said, inner product is a generalization of this dot product. So we can say that in general we can say that two vectors u and v are orthogonal if inner product uv is equal to 0. That is stated here. Two vectors are orthogonal if their inner product is 0. Now instead of two vectors, here we are taking a collection of vectors. A set of vectors is orthogonal if two vectors in the set are orthogonal. That is, if we consider any two vectors in that collection, they will be orthogonal to each other. Orthogonal basis means is a basis for a vector space in which all the vectors in the basis are orthogonal. An orthonormal basis is an orthogonal basis in which all the vectors in the base have norm 1. Norm means the length 1, that is the collection of all orthogonal bases. Orthonormal basis means it must be an orthogonal basis. Also, norm of each vector in that base must be equal to 1. Let's consider one example. Let's consider R2, space R2 over R, and consider Euclidean inner product. So this is an, we can easily verify that 1 by 2 0 0 1 by 2 is an orthogonal, is a basis. Now we need to check that whether they are orthogonal or not. So here we are considering one vector u is equal to 1 by 2 0 and another vector v is equal to 0 1 by 2. So we need to show that we can easily verify that collection UV is a basis of R2. We need to verify that this U and V are orthogonal or not. So here we are considering R2 with Euclidean inner product, that is inner product U V is equal to U1 V1 plus U2 V2. So here U1 V1, that is 1 by 2 into 0 plus 0 into 1 by 2, which is equal to 0. So inner product of U and V is equal to 0 means U and V are orthogonal to each other. So here this is a basis as well as they are orthogonal vectors. So this basis is a orthogonal basis of R square. But it is not an orthonormal basis. For that, let's consider norm u. What is norm u? Norm u is equal to square root of u1 square plus u2 square, which is equal to square root of 1 by 2 the whole square plus 0 square, which is equal to 1 by 2, which is not equal to 1. So its length is not equal to 1, therefore it is not orthonormal. This vector is not orthonormal. So we can say that this basis is not an orthonormal basis of R square. It is an easy example. You can simply verify that the standard basis of R square, that is 1 0 0 1, is an orthonormal basis of R2. Also in R3, this standard basis is an orthonormal basis of R3. That is, if we take this 1 0 as U and this 0 1 as V, we can show that they are orthogonal as well as their norms are equal to 0. If we take this 1 0 0 as U, 0 1 0 as V and 0 0 1 as W, we can easily show that inner product UV is equal to 0, inner product UW is equal to 0 and inner product VW is also equal to 0. That is U, V, W are orthogonal set. Also they form a basis of R cube. So this is an orthogonal basis of R cube. Also it is, we can verify that norm U square is equal, norm U is equal to 1, norm V is equal to 1 and norm W is equal to 1. So it form a orthonormal basis of R cube. Next is Gram-Schmidt process. By using this process, we can orthonormalize a set of independent vectors. These are the algorithm for that. These are the formula. Suppose we are given x1, x2, etc. xn as a basis for basis. So we will take v1 is equal to x1. Now to normalize this v1, we divide this v1 with its norm. So w1 is equal to v1 by norm v1. Now the length of w1 will be equal to 1, that is norm w1 is equal to 1. Now we take V2 is equal to X2 minus inner product X2 W1 W1, and to normalize this V2 we will divide V2 with its norm and we continue like that. Let's consider one example. Here we are considering 1 0 1 1 over r square. We need to find, by using Gram-Schmidt process, we need to find its corresponding orthonormal basis. So here we are considering 1 0 1 1. Let's take it as x1 and the second element as x2. So v1 is equal to x1. By using this formula, v1 is equal to x1. We need to take w1 is equal to normalize this v1, we need to take w1 is equal to v1 by norm v1. So what is norm v1 here? Norm v1 is equal to, we are considering Euclidean norm and Euclidean inner product. So norm v1 is equal to square root of 1 square plus 0 square, which is equal to square root of 1, right? So this is equal to v1 by 1. So it is 1 0 itself. Okay. Now let's consider v2. So what is v2? v2 is equal to x2 minus inner product x2 w1 w1. x2 minus inner product x2 w1 w1. Now we need to check what is inner product x2 w1. It is equal to, we know that w1 is this and x2 is this, so their inner product is 1 into 1 plus 1 into 0. So it is equal to 1. So inner product x2, therefore substituting in this formula, v2 is equal to x2, that is this 1 1 minus inner product x2 w1, we got it as 1 1 into w1, that is 1 0. So we will get it as 1 minus 1 is 0, 1 minus 0 is 1. So v2 is equal to 1. To normalize this, we need w2 is equal to v2 divided by norm v2, which is equal to 0 1 divided by square root of norm v2, that is 0 square plus 1 square, which is equal to 0 1 divided by 1, which is 0 1 itself. So corresponding to this basis 1 0 1 1, by Gram-Schmidt process we can find an orthonormal basis corresponding to this, which is 1 0, this w1, and next is w2, which is 0 1. That is our standard basis of R2. Okay. These are some practice questions. Try to work it out by yourself. Next is change of basis. A change of basis is a linear transformation that maps a basis for a vector space to another basis for the same vector space. This is the algorithm behind it. Let's consider one example. Find the matrix of change of basis P from the basis alpha to beta of R cube and use this result to find the matrix of change of basis from beta to alpha. So to construct this change of basis matrix P, so first we need to write each element in beta as a linear combination of elements in alpha. Okay, so you already know how to find a linear linear combination. So here -3, 2, -3, -3, 2, -3. Write this vector first as a linear combination of other vectors of alpha, that is 1, 2, 1. So C1 into 1, 2, 1 plus C2 into -1, 2, -1. -1, 2, -1 plus C3 into 1, 1, 3. Then try to find the arbitrary constants C1, C2, C3. Solving that, we will get it as -1, 2, 0. We will get C1 is equal to -1, C2 is equal to 2 and C3 is equal to 0. That's written here. This -3, 2, -3, we can write it like that as the linear combination of these three vectors. Now to construct P, we will write this coefficients as a first column of that matrix. That is, here it is -1, so we will write it here -1. Here it is 2, so 2. Then the next term is C3 is 0. So here the last entry of the first column is 0. Now take the next element 1, -1, -1 and write it as a linear combination of these three vectors of alpha. You will get it as 1, -1, -1. Now the second column of this matrix P will be this coefficient, that is 1, -1, -1. Then write this last element 5, 4, 9 as a linear combination of these three elements. You will get the arbitrary constants as 2, -1, 2. So the last column of the matrix P will be 2, -1, 2. Okay. So this is the matrix P that we use to change the basis alpha to beta. Now to change the matrix of change of basis from beta to alpha, we can, by using this P, we can find that matrix also, which will be P inverse. That is, the matrix of change of basis from beta to alpha is P inverse. That is, just take the inverse of this matrix. Okay. This is another example to change of basis. Find the matrix of change of basis P from the basis alpha to beta. Here we are considering the vector space M of R square, that is set of all matrices over R square. So to construct that P, we need to write this element of beta as a linear combination of elements of alpha. So take the first element 1, -2, 1, -2. This is the first element in beta. Try to write it as a linear combination of the elements in alpha, and solving it you will get it as this, that is 1 into 1 minus, that is first entry of element of alpha, plus 1 into plus 0 into second element of alpha, plus 1 into third element of alpha, plus 1 into the last element of alpha. Okay, now for now write the coefficients of these matrices as the first column, that is 1 0, that is corresponding to this second element of alpha, we have 0 here, so 1 0 1 1. Next take the second element of beta and write it as a linear combination of the 4 elements in alpha. You will get this. So corresponding to that we can write the second column of P like this. Now take the next entry of beta and so on. And finally we will get this matrix P. And to compute the matrix of change of basis from beta to alpha, just take the P inverse of this 4 by 4 matrix. Thank you.